Welcome to the office. We want to continue taking a look at section 21, and we want to look at our next theorem. Again, this is a theorem that you looked at in the computer explorations, and I believe it would be the fourth computer exploration that you were looking at, third or fourth, something like that. The angle bisector concurrence theorem. The three bisectors of the interior angles of a triangle are concurrent at a point called J, at a point J called the incenter. So my apologies for the pause there. I was looking at the point J and here it's labeled N. So I'm not sure why there's that mismatch, but call it N if you want to, or that maybe is inconsistent with what we saw later. Call it J down here. Doesn't matter. This is the point that they're referring to, though. Anyway, that point is called the incenter, which is also the center of the circle that is tangent to all the sides of the triangle. This circle that is drawn here is called the incircle. Right? It's the inscribed circle or the incircle. So this is a nice diagram which presents the items in our theorem here: the incenter and the incircle. Incenter, incircle. All right, at this point, we want to prove this theorem. And we're going to use this diagram as we write up our proof here. So let's take a look at this. We're going to present a two-column proof, as is mostly typical here. Not always, but mostly. So for our two-column proof, the first thing is we want to consider our givens, and our first given is the triangle itself. So let's consider the triangle ABC. Triangle ABC. Fantastic. That is given. The next thing that we want to consider are two of the bisectors. So we're going to consider the bisector of A and the bisector of C. So we're going to let AQ bisect angle A, and we're going to let, let's see, so AQ bisects A, CR bisect angle C. And this, of course, we know because of the angle bisector theorem. Sorry, the angle bisector existence theorem. And that would be theorem 11.8 if you would like to go find it. It's good to know where these things came from. All right, so now that we have that, we're actually going to apply the crossbar theorem, and we're going to apply it twice. And it's a little bit tricky, but according to the crossbar theorem, if we take some point in the interior of the triangle and we consider the line that goes from the angle to that point, when it goes across, it is going to intersect that opposite side. Fantastic. So in this case, we already have a line that we're interested in. So we just choose a point in the interior on that line. And according to the according to the crossbar theorem, we have an intersection. So really cool. So there's a lot of explanation as to what's going on here for this one step. And maybe we could have broken it down a little bit differently. So we have this point according to, right, this point is what we're interested in. Maybe we can call it Q prime according to the crossbar theorem. But that results in a new triangle, AQ prime C. Now we have this other line that we're interested in, CR. So if I want to, I can consider this triangle. Maybe let me highlight the triangle we're working in green. So we're working in this triangle, AQ prime C. And now what I want to do is I want to choose a random point here on this line that I already know of. And I want to recognize that according to the crossbar theorem, we're going to get an intersection, right? The line from C to this, right? The line that passes through that is going to intersect the opposite side of the triangle. And that gives us the point N. In particular, that gives us the intersection of AQ and CR. So what we can conclude by applying the crossbar theorem twice is that AQ and CR, those two lines intersect at N, this point here, and in particular, that point is inside the triangle ABC. So that's definitely of interest to us. It's inside of the triangle. All right, so yes, excellent. And this, again, is according to the crossbar theorem. And from our notes, that would be theorem 12.5. And we're applying that twice in order to find n. Once to find Q prime, and then once to find n. All right. Now we're going to create some new lines. And these lines will be, of course, very useful to us. But what we're going to create are the three perpendiculars. The perpendicular to AC that passes through N, the perpendicular to AB, which passes through N, and the perpendicular to CB, which passes through N. And those are each given by the perpendicular existence theorem. So three perpendiculars, we're going to create these 3 points. So let's let n, let's see here, n, give this point as x. So let nx, it's a line segment, be perpendicular to AB. And we're going to let n, let's see here, go y here, and y be perpendicular to AC. And then x, y, z, we will let nz, oh, these are all lines. Make sure we have good notation. Nz is perpendicular to BC. And this is given by the perpendicular existence theorem. And that theorem is 13.9 for easy reference there. All right, so once we have each of these, we have 3 new lines. The lines themselves aren't well, I suppose the lines are important, the line from N to X. We want to talk about the measurements of these lines. Now, we know that xn or nx and ny are the same distance because n itself lies on the bisector of angle A. And so the point on bisector theorem tells us that, all right, since it's on the bisector, we know that ny and nx have the same distance. Similarly, since n is on the bisector of C, we know that ny and nz both have the same distance. And ideally, nx and nz would be the same length or the same distance as well, because it would lie on the bisector of B, if we actually have concurrence, right? That's the idea. That's what we want to show. So we do have nx and ny are the same because of the point on bisector theorem, and we do have that ny and nz are the same length because of the point on bisector theorem. So we're using the bisector theorem in one point on bisector theorem in one direction there. But then by the transitive property of equality, these two things are equivalent in length, telling us again by the point on bisector theorem, the other direction, that n is on the bisector of B. And then we're done. So we've created these 3 new lines to observe the distances and utilize the point on bisector theorem. So a couple of things here. Nx is equal to ny. So number 5, fifth step here. Nx is equal to no line there. Nx is equal to ny. That is a distance measurement. And we also have that ny is equal to nz. And these are both because of the point on bisector theorem. And that's theorem 13.12. Now, in this case, we're using the forward direction of the bisector theorem. You don't have to make such notes, but I'm just trying to help us understand as best as possible. Sixth step is that transitive property of equality. We get that nx equal to ny equal to nz is equal to nz. These two things are equal by the transitive property of equality. That's fantastic. All right, step 7 then is using the point on bisector theorem in the other direction. Since the two distances are the same, then this must be on the bisector of B. So N is on the bisector of angle B. And again, this is the point on bisector theorem. Again, theorem 13.12, but we're using it in the opposite direction because it's an if and only if statement. And then we're essentially done, right? N is on the bisector. We just have to state the thing that we want to know. And since N is on the bisector, we know that the three bisectors are concurrent. So the bisectors of angle A, angle B, and angle C are indeed concurrent. And that's simply by the definition of concurrence. Right, they have a single point in common. What is that point? That is the point N in our diagram above. Fantastic. Thank you for your time and your attention. We'll take a look at one more theorem for this section that we want to prove, and then we have some more computer explorations, actually. So another theorem in just a minute. I'll see you guys back in the office.